Field maps show the electric field, which is the invisible field of influence from one or more charged particles, and we can ignore the charged particles that cause that field of influence. There are different representations, and each of these will emphasize a different aspect of the field. In this first image, we can see a vector plot. Vectors have been drawn in an array, and the length and the direction of these vectors indicate the electric field at each of those points. This next image shows a stream plot. The stream plot emphasizes the direction of the electric field. The electric field points along those streams. In this third image, we've got a contour plot of the same electric field. The contour plot shows the magnitude of the electric field. You can see that it's weakest in the center, where the dark disk is, and it increases as you get further out from the center. Now, of course, space is three-dimensional, so a full picture of the electric field actually needs to be in 3 dimensions. And you can see that same field represented in 3 dimensions here. Let's say we want to make a map of the electric field, that is the force that's going to be felt by our test charge uppercase Q. And that field is going to be caused by 2 charges. We're going to put a charge at the origin and another one at point 2, 0, along the x-axis. You can see in this diagram here, I've indicated the electric field in blue due to the charge in the origin, and the electric field in red due to the charge on the x-axis at position point 2. You can see the way we've done this is we've moved Q to different positions, and now what we do is we will add those forces as vectors. So we have 2 forces at each position, 1 from each charge. So in other words, we have a total electric field that results from the superposition of the electric field from each charge. Now, it's very time consuming to calculate the force at every position due to 1 charge. And now it takes even longer because we have to calculate 2 forces and then add them as vectors. Imagine how time consuming it will be if we have a lot of charges, and that's realistic. You think how many billions of electrons you have on the head of a pin. Now, up to a point, a computer can handle this summing, but we humans can't. That's why we're going to use Gauss's law. It's a useful trick to relate those charges and the electric field. I'm introducing you to Gauss's law. Now, Gauss's law states the electric field flowing through the surface of any 3D shape is proportional to the charge inside that volume. Sounds useless, but we'll see how you can use it. Let's remind ourselves. The electric field flow through the surface of a 3-dimensional shape is proportional to the charge enclosed. And that constant of proportionality happens to be, mysteriously and simply, 1 over epsilon naught. This first diagram shows I've put a sphere around those 2 charges. One's at the center, the other's close to the edge on the right. This next image shows the electric field calculated at the surface of that sphere. The arrows show the strength and the direction of the electric field. you can see how the electric field is flowing out of this particular sphere. Now, the sum of the flow through the surface has a very specific term in physics. It's called the flux, and we're going to calculate it with a surface integral. Let's take a three-dimensional surface, such as a sphere, and we'll take a small element of area. Believe it or not, area is also a vector. It has a direction, and that direction is at right angles to the surface. It has an area dA of magnitude, and of course this, if we include this little vector symbol, we can see that it is actually a vector. If we work out the electric field at this point, at this particular point here, might be pointing in this direction, say, then we can work out what is the microscopic flux just at that point there. That's going to be the electric field at that point dot the area element vector. If we add up over the whole surface, of course, we do a sum like that. This is called the flux. It's just another word for flow. So that's going to be how we calculate our electric field flux. You can find more notes in your lectures in Maths for Physical Sciences or your vector calculus notes to find a better description. Okay, so we've worked out our electric field flow. Now, it's easy enough to work out the charge enclosed, isn't it? The charge enclosed might be discrete point charges, so it's easy enough to add them up. We just sum over each of those charges. Alternatively, the charge might be distributed, like on the plate of a capacitor. In that case, we're going to need to take the volume and multiply it by the charge density. So the charge density will give the symbol ρ, and that has units of coulombs per meter cubed. We'll multiply it by the volume element and integrate over the whole volume. So now you can see we have Gauss's law. Gauss's law says the electric field dotted with the surface element, integrate that all around and we'll get the flux, is equal to the total charge enclosed times the constant of proportionality.